In this lecture, let us see about the analysis of pre-stressed concrete beams under flexure. So, what is flexure? Flexure or what is flexural stresses? Flexural stresses are nothing but the stresses induced in the concrete beam due to the action of external loads, and in our case even the pre-stressing force. In this lecture, I have discussed about the flexural stresses in the beams with two types of tendons. One is concentric tendon and the eccentric tendon. So what is concentric tendon? Concentric tendon is nothing but the tendon which is placed along the axis of the member, in which there is no eccentricity placed. So we call this type of tendon as concentric tendon. So let us consider a concrete beam of total area A and a pre-stressing force P applied on the tendons which are placed concentrically. So this is the concrete beam, and this is the force acting on the tendons which are placed concentrically. Then the stress resulting from such kind of tendons are directly due to the pre-stressing force acting on the beam. We call it as direct stress. So the direct stress due to the pre-stressing force will be P by A, where P is the magnitude of pre-stressing force and A is the area of the concrete beam. This stress will be acting compressively, or it will be in compressive nature all over the beam. So next case is the flexural stresses in the beam with the eccentric tendon. So what is eccentric tendon? If the tendon is placed with an eccentricity, let us consider this eccentricity as E, we call such tendons as eccentric tendons. So let us consider a concrete beam with a total area A and the pre-stressing force of P applied on the tendons which are placed eccentrically. Let E be the eccentricity of this tendons. So as we see, this is the tendon which is placed with an eccentricity E from the axis of the member, on which the pre-stressing force of magnitude P is acting. So because of the eccentricity present in this beam, we have an additional stress called as bending stress. So one is the direct stress and the other one is the bending stress. Direct stress of acting on the beam due to the pre-stressing force is again compressive in magnitude of P by A, and the newly acting bending stress due to the pre-stressing force acting eccentrically is tensile at the top fibers and compressive at the bottom fibers of the section. So the value of this stress due to the bending moment M is M by Z. So we consider as M by ZT, where ZT is the section modulus in the top fibers in the top of the section, and M by ZB, where ZB is the section modulus of the bottom fibers in the bottom of the section. The magnitude of M moment will be equal to the product of pre-stressing force P and an eccentricity E. So this is the distribution of direct stress, which is taken as compressive distributed all over the section. We consider the compressive stress as positive and the bending stress of negative or tensile in nature at the top, and compressive or positive at the bottom section of the given beam. So this will be the resultant stress distribution of magnitude P by A minus PE by ZT at the top, and P by A plus PE by ZB at the bottom section of the given beam. So let us see an example or a problem based on this analysis. So a pre-stressed concrete beam of section 200 mm wide, 300 mm deep, with an effective span of 6 meters is imposed with a load of 4 kN per meter. Density of concrete is 24 kN per meter cube. At the center of span, find the magnitude of concentric pre-stressing force necessary for zero fiber stress at the soffit of beam when it is fully loaded. So let us sort out the given data first. So he has given the width of beam B as 200 mm and depth of beam D as 300 mm, effective span L of 6 meters, and imposed load of Q of 4 kN per meter, and density of concrete as 24 kN per meter cube. So let us calculate the preliminary data required to solve the problem, such as area and the section modulus. So where area will be breadth into depth, that is 200 into 300 mm, which is equal to 6 into 10 power 4 mm square. And the section modulus, we all know that the section modulus for a rectangular section is BD square by 6. So as it is an uniform section, ZP will be equal to ZT, so which is equal to 200 into 300 square by 6, equal to 3 into 10 power 6 mm cube. Let us calculate the dead load of the given section, which is equal to the product of the dimensions of the beam into the density of concrete. So that gives a total dead load or the self-weight load of magnitude 1.44 kN per meter cube. And calculating the moment due to this dead load, if we consider it as a simply supported beam with an UDL, the maximum moment is WL square by 8 at the center. So this is W into L square, which is 1.44 into 6 square divided by 8, that is into 0.125, will give you 6.48 kilonewton meter. This is due to the dead load. This is the moment of magnitude 6.48 kilonewton meter due to the dead load. So let us calculate the moment due to the live load also. He is already given the live load as 4 kilonewton per meter, that is imposed load. So WL square by 8 will give you a moment of magnitude 18 kilonewton meter due to the live load. So let us calculate the total stress due to the dead load and live load at the bottom fiber. So which will be M by Z. So 6.48 plus 18, we convert into the Newton and meters, it is into 10 per 6 divided by the section modulus, that is 3 into 10 per 6, will give a tensile stress of magnitude 8.16 Newton per mm square. So in the question it is already, he is asking for the magnitude of the concentric pre-stressing force. So here we need to observe that it is a concentric pre-stressing force. So we have only direct pre-stress acting in the member. So he's asking the magnitude of that concentric pre-stressing force, which will nullify the stresses present in the beam. So if this is the stress present in the beam, the applied pre-stressing force should nullify this stress. So what will be the direct pre-stress value, that is P by A, should be equal to this stress. So P by A will be equal to 8.16, and we already know the area of the section A, that is we have calculated it here as 6 into 10 power 4. So from here, if at all we multiply that 8.16 into 6 into 10 power 4, we'll be getting a pre-stressing force of magnitude 489.6 kilonewton. So hence, if at all we apply a pre-stressing force of magnitude 489.6 kilonewton, concentrically we'll be able to nullify the stresses due to the dead load and live load that is acting on the beam. So the next concept is analysis of pre-stressed concrete beam with a bent tendon. So why should we go for a bent up tendons? So bent tendons are used in pre-stressed concrete beams, as they tend to provide an upward pressure in the beam and they reduce the effect of external loading to a great extent. So if at all we consider a concrete beam of length L subjected to a point load of intensity W kilonewton at the center, and a pre-stressing force of P is applied at the ends. So this is the beam with a bent tendon of angle theta at the center. Let the beam be named as AB. So as the load is acting downward, there will be obviously a reaction from the tendon, which will be in the opposite direction, that is upward. So the tendon will develop an upward force of magnitude 2p sine theta at the center of beam. So net upward force will be, so there will be a force developed upward here, so which is equal to magnitude 2p sine theta. So the net upward force will be W minus 2p sine theta, and the longitudinal force along the tendon will be 2p cos theta. So direct stress will be remained constant as a P by A, and the bending stress is M by Z. But here the M value will be differ as F into L by 4, that is W into L by 4 in normal case, but here the value of F will be W minus 2P into sine theta, and the resultant stress will be summation of P by A and the bending stress, that is M by Z. So which is M by Z will be as usual tensile in nature in the top fibers and compressive in nature at the bottom fibers. Thank you.